Hello everyone. In this video, we're going to go over a review for Math 1050 chapters 2 and 3, covering polynomials and rational functions. I'm just going to go through some practice problems and talk about some basic principles. So first up, something we like to have you do, we had a similar problem on our last test, is sketching quadratics. Now, to sketch a quadratic, an important thing to remember is what the basic quadratic looks like. It has a vertex at 0, 0. So I'm going to note that in black is q of x equals x squared. So we have a vertex at 0, 0. And then it goes over 1, up 1, since 1 squared is 1. And what's interesting is the perfect squares are actually the sum of odd numbers. So what does that mean? To get to the next perfect square, I go over 1 and up 3. Because 2 squared is 4. Then I'd go over 1 and up 5 if I had more room. And then it's symmetric, so the basic x squared graph looks something like this. Now, let's look at what we've done to it. First off, we have x minus 3 squared. Remember, I'm going to do my changed one in purple. Remember, that means our vertex has an x value of 3 because everything in the parentheses goes opposite of what we think. Or you can think of it as what makes the thing in the parentheses 0. And then we have that plus 4, which means the vertex is at 3, 4. So we have our vertex. Now, one requirement I generally have in my classes is 3 good points on a graph. So now we have one good point. So what do I mean by a good point? It's one that's clearly marked on the graph. I can tell exactly where it is. I don't have to guess. Additionally, it's on graph paper. If you're on an online class, make sure you're using graph paper for your tests. It'll make it a lot easier for us. Now, how do I get 2 other good points? Well, remember, in our basic quadratic, I went over 1, up 1. This -2 is a vertical stretch. It flips it and stretches it. So in other words, I'll still go over 1 to get a good point, but instead of going up 1, I'll go down 2 because of that -2. So I go over 1, down 2. And since they're symmetric, I do that on the other side. So there are my 3 good points, and I can just draw the shape. If I want to be a little extra, instead of going over 1 and up 3, as we did for the second point in the basic, I'll go over 1 and down 1, 2, 3, 4, 5, 6. Because I'm taking that 3 that I usually go over 1, up 3, and multiplying it by -2. So now I even have 5 good points. And I can connect the dots and make the basic shape. So that's how we sketch a graph of a quadratic written in vertex form like this. Next, this next practice problem asks us to describe the end behavior of a polynomial. Now, remember, end behavior depends completely on the leading term. Because in the long run, x to the 4th is going to beat x to the 3rd, no matter what's multiplied onto it. Even if this is like minus a billion x cubed, the x to the 4th is going to beat it. So let's remind ourselves our rules for end behavior. For end behavior, we look at the leading term. And the first thing we look at is the degree. So if the degree is even, my end behavior is either double up or double down. If it's odd, they're opposite. Either down on the left and up on the right, or up on the left and down on the right. So now the question is, which of these 4 options am I going to use? Well, The other thing that we look at is the sign of the leading coefficient. And so if the leading coefficient is positive, we use this column. If the leading coefficient is negative, we use this column. So let's see, we have an even degree, but an odd leading coefficient. So we have what I like to call double down end behavior. But we want to write that in a formal way. The formal way we write that is as x goes to positive infinity, or in other words, as I look on the right side of the graph, the polynomial, the y values of the polynomial are going to negative infinity. So to kind of write this in less formal terms, this means on the right, I'm going down in the long run. And then I want to talk about what's going on the left from the one we highlighted. We know it's left and down. And so the formal way we say that is as x goes to negative infinity, p of x goes to negative infinity. So notice that for the y values or the outputs, for down, I use a negative infinity. If it were up, I'd use positive. And then with the x values, right is positive infinity, left is negative infinity. If you're in my class, I do want the formal notation. All right, now let's sketch a rough graph of a polynomial in factored form. Now, a good thing to do first is to check the end behavior again. Now, I don't have the leading term, but I can count factors, because for each factor, I get an extra degree in the polynomial. So here I have one factor. Since the x plus 1 is squared, I get 2 more factors. Since the x plus 5 is cubed, I get 3 more factors. So this is a degree 6 polynomial. So it's even degree. And since there's no negatives that'll show up on the x's, it will have a positive leading term. So which one is that? If you look at our table on the previous question, that means our end behavior looks like this. Now, a lot of crazy stuff can happen in the middle here. To figure that out, we look at the zeros. And remember, zeros and factors go hand in hand. I just solve where each factor is equal to 0. 3x minus 2 equals 0 when, let's see, that means 3x equals 2. So x equals 2/3. I'll solve where x plus 1 equals 0. Don't know why I put that other equal sign there. I can subtract 1 from both sides, and I get x equals negative 1. And similarly, for x plus 5 equals 0, I get x equals negative 5. So I'm going to mark those in purple on my graph. So here's my 2/3. Here's my negative 1. And here's my negative 5. Now the question is, what does the graph do at those zeros? And we have 3 options. So at our zeros, or at our x-intercepts, a graph can just straight cross, just go through it, nothing special. It can bounce, which means it changes directions at the x-intercept, or it can do what I call a shimmy, where it crosses, but it flattens out. Now, how do we tell? By the multiplicity of the zero, or the degree on the factor. So a cross comes from a first degree factor. A bounce is a second degree. And you guessed it, a shimmy is a third degree. Now this pattern continues where all even degrees are bounce and all odd degrees are crosses, with odd degrees higher than 1 having the flatten and cross shimmy. But in this case, I probably won't do above degree 3. So let's go ahead and draw that. I know since it has double up end behavior, I'm going to start up here. And then I'm going to go down to the x plus 5. Now, since x plus 5 is cubed, that tells me that at x equals negative 5, I have a shimmy. So I'm going to go down. I'm going to make the graph flatten a little bit and then continue down. It's a flatten and cross. Now, we know the graph is going to have to curve back at some point. We don't care where in this class. And if you take calculus, you'll actually figure out where it turns around. But now I look at the x equals negative 1. Well, that one is squared. So we're going to have a bounce because it's a squared factor. So I bounce here. And then once again, I'm going to have to turn around and come back. And at 2/3, since it's degree 1, since there's no exponent on the factor, it's just a simple cross. And it just keeps going. Now, this is a very rough graph because if I found the y-intercept of this, its y-intercept would actually be negative 250. And this local min over here could be lower or higher than that. We don't know. All I care about are the x-intercepts and the behavior of the graph near them. Am I crossing? Am I bouncing? Or am I shimmying? Next, we're going to do that again with a longer function. But we're going to specifically identify the x-intercepts. So notice here, intercepts and factors go hand in hand. So for x plus 1, I solve x plus 1 equals 0. So x equals negative 1. And since that factor's squared, the graph is going to bounce at that 0. So the 0 is negative 1. The x-intercept is negative 1, comma 0. So remember, an intercept is a coordinate. A 0 is just a number. Next, I'll do the x plus 3 equals 0. I get x equals negative 3, and that's going to bounce. X minus 4 equals 0. I get x equals 4, and that's going to cross because it's degree 1. 2x minus 5 equals 0. Let's see, that means 2x equals 5. So x equals 5 halves, and that once again is going to cross. So my x-intercepts are negative 1, 0, negative 3, 0, 4, 0, and 5 halves, comma 0. Now, I can use that to draw a very rough graph. So let's see, we'll say this is negative 1. That means negative 3 would be about here. 5 halves is about 2.5. So that's going to be, let's see, there's 2, there's 3, so it'll be right there. And then 4, my other cross will be right there. So this 2x to the 6th for n behavior, this tells me it's a double up because it's an even power with a positive coefficient with a positive in front. So this graph will start up here on the left and come down to this negative 3. We know it bounces since the companion factor is squared. Turns around, it bounces at negative 1. And then at 5 halves, it's going to cross. And at 4, it's going to cross because those are degree 1 factors. Once again, this is super rough. All I'm looking for are x-intercepts. All right, let's do polynomial long division, everyone's favorite thing. Now, we use it for a lot of reasons, but a common one is to find a slant asymptote for a rational function. Since this is x squared, we have to do our classic polynomial long division, where I do x squared plus 3x plus 1 goes into 4x cubed plus 7x squared minus 11x minus 5. And remember, degree drives division. We say, what do I multiply the highest power term of the divisor by to get the thing on the highest power term in here? And in this case, it would be a 2x. Or excuse me, a 4x. I don't know where I got the 2. And so I end up with multiplying that 4x by the divisor. So I get 4x cubed plus 12x squared plus 4x. And I subtract all of that, just like we do in classic long division. So remember, this is 7x squared minus 12x squared, which gives us negative 5x squared. I should note that the 4x cubed minus 4x cubed goes to 0, so we don't even write the result. And negative 11x minus 4x gives us negative 15x minus 5. Now, what I'll do is I'll say, okay, what do I have to multiply x squared by to get to negative 5x squared? And so in this case, that'll be negative 5. And so I'll have negative 5x squared minus 15x minus 5. Well, this is a special problem because the remainder is 0. But guess what? For a slant asymptote, we don't care about the remainder. All we care about is the quotient, the result. And so since we got a quotient of 4x minus 5, this means in the long run, this function will behave like y equals 4x minus 5. Because that was the quotient when we divided. Because in general, the quotient plus a small remainder is going to look a lot like the quotient, a lot like the thing that's the 4x minus 5 up there. All right, let's talk about possible rational zeros. So remember, I'm only finding possible rational zeros. This is a very short question. To find possible rational zeros, it's the factors of the constant term divided by the factors of the leading coefficient. In this case, that's, and we also want to have a plus or minus on all of them. So in this case, we're going to look at factors of 10 over factors of 2. Now, the factors of 10 are plus or minus 1, plus or minus 2, and plus or minus 5. And the factors of 2 are plus or minus 1 and plus or minus 2. So I could always have the factors of 10 divided by 1. So my possible rational zeros include plus or minus 1, plus or minus 2, and plus or minus 5. They also include all of those divided by 2, which gives me plus or minus 1/2. 2 divided by 2 is 1, which I already have, and plus or minus 5/2. Now, why do we care? Well, if we're looking for zeros, I've narrowed it from all rational numbers, an infinite number, to just 10 to check. And as you might guess, that's what we're going to do on number 7. Now, to help us do that, let's once again write the possible rational zeros. So it's the factors of 12, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12, divided by the factors of 3, which are just 1 and 3. So I'm going to have all of those, and then each of those divided by 3, plus or minus 1/3, plus or minus 2/3. 3 divided by 3 is 1, so I don't need that. 4 divided by 3 is 4/3. 6 divided by 3 is 2, and 12 divided by 3 is 4, and I already have those. Now the question is, where do we start? So these are all the possible rational zeros, and we want to see which ones work. And that's where we use synthetic division here. That's the goal of synthetic division, is to find zeros that work. Now, the question is, which one do we guess first? Well, I often try to figure out if 1 will work, and so I kind of mentally put 1 in and say, okay, 3 plus 2 minus 37 plus 12. Is that going to be 0? No, it's not. -1? I doubt it. That 37 is just too big. So we want to try something like 2 or 3. So let's go ahead and try 2. And remember, I write the coefficients across the top. So I bring down the 3, I multiply it by 2 to get 6. 2 plus 6 is 8. 8 times 2 is 16. Negative 37 plus 16 is negative 21. Times 2 is negative 42. Yeah, this isn't going to work. So I can say, yeah, that's not going to work. So maybe 3 will work. So I do the 3, the 2, the negative 37, and the 12. I bring down the 3, I multiply by 3, I add the 2 and 9 to get 11. I multiply by 3 to get 33. Oh, I feel good about this. I get a -4. -4 times 3 is -12. And I get a 0. So this tells us if I run 3 through this left-hand side, I'll get 0. And even more than that, this tells us that this polynomial factors into x minus 3, the factor that goes with a 0 of 3, times 3x squared plus 11x minus 4, the part that's down there on the bottom. Now, 3x squared plus 11x minus 4, that's a quadratic. We can use quadratic formula or our factoring skills to solve for the zeros of this one. Now, I look at this one and I think it actually factors. So I think of two numbers that are going to multiply to -12, the 3 times the -4. So that -12 comes from the product of those two numbers. And that adds to 11. And so those two numbers are going to be 12 and -1. And so that means 3x squared can be written as 3x squared plus 12x minus x minus 4. I like to use the box method to factor. It helps me group a little easier. So I put a 3x squared here, a 12x here, a -x down here, -4 down here, and I say, okay, what goes into both 3x squared and 12x? Well, a 3x does. And 3x times x is what must have given me 3x squared. Oh, I have a -x down here, so this must be a -1 on this side. -1 times 4 is what gives me -4, and let's check. 3x times 4 is in fact 12x. So that means this factors to 3x minus 1 times x plus 4. So that gives me my other two zeros. I have x equals -4. And then 3x minus 1, I always like to solve that to make my life a little easier. I add the 1. I divide by 3, and I get x equals 1/3. So in the end, we end up with solutions of x equals 3 from our synthetic division, and then 1/3 and -4 from factoring our quadratic. Wasn't that fun? And then just for funsies, let's practice our long division. Now, there's a tricky part in here because notice there's no x cubed. So I'm going to rewrite this as x to the 4th plus 0x cubed minus 2x squared plus 3x plus 5 divided by x plus 2. And I say, what do I multiply x by to get to x to the 4th? And that's an x cubed. Let me move this down a little bit so I'm not writing on top of text. So I end up with a x to the 4th plus 2x cubed over here. I subtract all that and get a negative 2x cubed here. And I'll bring everything else down. Now, what do I multiply x by to get to negative 2x cubed? Well, that's a negative 2x squared. So I have a negative 2x cubed minus 4x squared. I subtract all of that. And I end up with a positive 2x squared. Because remember, this is negative 2 minus negative 4, which is the same as adding 4, plus 3x plus 5. Okay, what do I multiply x by to get to 2x squared? That's a 2x. So I have 2x squared plus 4x. I subtract all that to get a negative x plus 5. So what do I multiply x by to get to negative x? Well, that's a negative 1. Since this is a constant term, this must be my last division term. So I have negative x minus 2. I subtract all of that. I apologize, that parentheses is in the wrong spot. I subtract all of that. And in the end, I get a remainder of 7 because I'm subtracting a negative 2. So in other words, I can say that the answer is x cubed minus 2x squared plus 2x minus 1 plus 7 over x plus 2. We'll check that using synthetic. We can do synthetic since this is just x plus or minus something. So what's the 0 that goes with that? It's a negative 2. I'll write all my coefficients. 1x to the 4th, 0x cubed, negative 2x squared, 3x, and 5. Then I add down and multiply up. And so let's see, negative 2 times negative 2 is 4. I add the negative 2 and the 4 and get positive 2. 2 times negative 2 is negative 4. 3 plus negative 4 is negative 1. Negative 1 times negative 2 is 2. 5 plus 2 is 7. And that matches because I have that 1 is the same as the 1x cubed. Negative 2 times x squared plus 2x minus 1 plus a remainder of 7 over the divisor. So that all checks out. All right, let's use the rational root theorem to list all possible rational roots of this equation. Once again, we look at the factors of the ending term plus or minus 1, plus or minus 3, plus or minus 9, and then divide them by the factors of the leading term, 2. And so I'll have a plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. Now, the first thing I notice here is that I have a 2 and a 9 and a negative 2 and a negative 9. So that makes me suspect that that 1 will be a 0 of this polynomial. And so let's go ahead and do that. So I bring the 2 down. 2 times 1 is 2. 9 plus 2 is 11. 11 times 1 is 11. Negative 2 plus 11 is 9. 9 times 1 is 9. And negative 9 plus 9 is 0. So that means this must factor to x plus 1 times 2x squared, or excuse me, 2x minus 1. Since it was a positive 1, I need to have it be a factor that makes it 0. 2x squared plus 11x plus 9. Now, since this is a quadratic, I can use the quadratic formula or whatever else I want to find what makes this 0. I'm going to factor it just because I like factoring. And so I say, okay, what do I multiply together to get 18, but also add to get 11? Because remember, I have to multiply the 2 and the 9 to figure out my multiply 2 number. And looking at these, the two numbers that work are 2 and 9. So this is 2x squared plus 2x plus 9x plus 9 equals 0. And I'll go ahead and factor by grouping. I'll look at what goes into these two, which is a 2x. And I'm left with an x plus 1. What goes into both of these is a 9. And so I have a plus 9. And since the x plus 1's match, I know I did this right. If they didn't match, I must have done it wrong. But since they match, I'm good. So I get 2x plus 9 times x plus 1 equals 0. So in the end, my zeros are 1, negative 9/2, because that's what makes 2x plus 9 equals 0, and negative 1. Those are my 3 zeros. Next up, we get to graph a rational function. Now, let's remember a couple things. First off is rational functions, we always have to check for horizontal and vertical asymptotes. Vertical asymptotes come from divide by 0 errors, because dividing by numbers really close to 0 get us really large numbers approaching infinity. So vertical asymptotes here are going to come when I have x plus 1 equal to 0. Well, that's when x equals negative 1. So that's one of our asymptotes. Now, our horizontal asymptotes come from long-run behavior, which, just like with polynomials, is determined by highest power terms. So in the long run, this function is going to behave as if it's the leading term of the top divided by the leading term of the bottom, which in this case is 2. So my horizontal asymptote is y equals 2. Now for x-intercepts, those come from when factors are 0, specifically factors on the top. Because remember, dividing by 0 gives us an asymptote, but dividing 0, doing 0 divided by something, is just 0. If that seems weird, think about what would happen if I had $0 and shared it amongst 10 people. How many would each get? $0. It's doable. But if I say I have $10 I want to share with 0 people, that doesn't make sense. Where does the money go? So 2x plus 4 equals 0. I can subtract 4, so I get 2x equals negative 4. So x equals -2. So my x-intercept is -2, 0. Y-intercepts are where y is 0, or where x is 0, excuse me. So I'll do 2 times 0 plus 4 over 0 plus 1. Hey, that's just 4 over 1, which is 4. So that means my y-intercept is 0, 4. So now I'm going to use that information to help plot the graph. So there's my x-intercept, -2, 0. Here's my y-intercept at 0, 4. I have an asymptote at -1 and a horizontal, or at x equals -1, and a horizontal asymptote at y equals 2. The main thing to remember when graphing rational functions is that you follow the asymptotes. Now, the question is, often, with the horizontal asymptote, am I following it above the asymptote or below it? Now, the answer for this one comes from this point right here. Since I have this x-intercept here, that means I must be below the asymptote. I hit my x-intercept, and I have to follow the vertical asymptote and go down. We usually switch directions on the vertical asymptote, and I'm going to hit my y-intercept and follow this out. So follow point, or plot points, follow asymptotes. All right, let's jump back to a polynomial question. Notice on this one, I'm told that x equals 2i is one of the zeros. The question is, what are the other zeros? So, remember, we have something called the conjugate pair theorem, where if 2i is a 0, x equals -2i is also a 0. It has to be. That's the only way for us to not have any i's in this polynomial right here. So that means what I get when I multiply x minus 2i plus x plus 2i together must be a quadratic that factors out of that cubic. And if I multiply that out, I actually get x squared minus 2ix plus 2ix minus 4i squared. Those 2ix's subtract out, so I get x squared minus 4 times I squared. As a reminder, I squared is -1, so this turns into x squared plus 4. So this cubic is x squared plus 4 times something. Well, let's divide out x squared plus 4. So I have x cubed minus 3x squared plus 4x minus 12. What do I multiply x squared by to get to x cubed? Just an x. So I have x cubed plus 4x. I subtract all of that, and I'm left with -3x squared minus 12. What do I multiply x squared by to get to -3x squared? A minus 3. So I get another -3x squared and another minus 12, which is good because I should get a remainder of 0. And so I end up with x minus 3 as my other factor. So f of x is equal to x minus 3 times x squared plus 4. But what does that mean? That means my other 0 is whatever makes x minus 3 0, or just x equals 3. So in the end, my other zeros are x equals 3 and -2i because of the conjugate pair theorem. And that's it for that problem. All right, let's do an application. Quadratics are often used to model vertical motion. So if a ball is thrown vertically upward, its height in feet t seconds after being thrown is given by that quadratic. When does the ball reach its maximum height? Well, it comes at the vertex of the polynomial, which always happens at negative b over 2a. So when does it occur? When the time is negative b over 2a, or in this case at 48 divided by 2 times negative 16, which ends up being 48 over 32, which is 3/2 or 1.5. So when does it reach its maximum height? 1.5 seconds after being thrown. So how do I find that maximum height? Well, I have a function relating height and time. So if I plug that 1.5 in, that should tell me the height. So I have negative 16 times 1.5 squared plus 48 times 1.5 plus 10. So that gives me negative 16 times 2.25, because that's 1.5 squared. 48 times 1.5 is 72. If I do negative 16 times 2.25, it ends up giving me a negative 36. And so in the end, this equals 46. So its maximum height is 46 feet. Remember, units matter, so if you don't write the units, points will be taken off. All right, let's write a polynomial given some information about it. It's a third-degree polynomial with integer coefficients with real roots that are -1 and 2 with multiplicity 2. Now, what does that mean? That means that the factor that goes with 2, which is x minus 2, must be squared. So we'll call this f of x. And so it seems like we're done. But let's check f of x. Let's check if f of 0 equals 8. F of 0 equals 1 times negative 2 squared. Uh-oh, that equals 4. So we did something wrong, or we're missing something. So I need to somehow modify this so I get a y-intercept of 8 without changing the zeros. So I just multiply by a constant, because multiplying by a constant won't change the zeros. So that must mean f of x equals a, some number a times x plus 1 times x minus 2 squared. Now, what is that a? Well, let's plug in f of 0. And as we know, that x plus 1 times x minus 2 squared, when I plug 0 into there, I get 4. So f of 0 is a times 4, whatever that leading coefficient is, times 4. Well, we know that's supposed to equal 8. So I can divide both sides by 4, and a equals 2. So my final answer is f of x equals 2 times x plus 1 times x minus 2 squared. And that's the answer to that one. All right, now we're going to practice finding the zeros of a fourth degree, which is really, really fun. Once again, I'm going to list the possible zeros by looking at the factors of the constant term. Since the leading coefficient is 1, I only need to look at the factors of 54, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18, plus or minus 27, and plus or minus 54. So how do I know where to start? I usually like starting with positive numbers, especially something you may have learned about is the sign change rule. Since this polynomial, the terms go from positive to negative, so that's one sign change. And then from negative to positive, that's another sign change. And from positive to negative, that's a third sign change. This is going to have 3 or maybe 1 positive 0. So it's the number of sign changes minus an even number, because there could be some non-real zeros that throw things off. So I'm just going to try some things. It looks like 1 isn't going to work, so I'm just going to go ahead and try 2. So let's see, 1, -1, 3, -9, -54. So I have 1. 1 times 2 is 2, so I get another 1. 1 times 2 is 2. 3 plus 2 is 5. 5 plus 2 is 10. I don't think this is going to work. -9 plus 10 is 1. Nope, this isn't going to work. So let's try 3. Okay, bring down the 1. 1 times 3 is 3. -1 plus 3 is 2. 2 times 3 is 6. 3 plus 6 is 9. 9 times 3 is 27. -9 plus 27 is 18. 18 times 3 is 54. And that gives me a 0. All right, so I know one of the zeros, and also since my new ending term is 18, everything above 18 is automatically disqualified from being a 0. So and 2 can't be a 0 because it wasn't a 0 of the original fourth degree polynomial. So 3 worked. Let's try something else. I feel like I see a lot of doubles here, like 1 times 2 is 2, 9 times 2 is 18. So let's try a -2. Since all these numbers are positive, this tells me that all my zeros have to be negative from here on out. I can't get to 0 by adding positive numbers together. So let's try a -2. So I bring down the 1 times -2 is -2, which gives me 0. 0 times -2 is 0. 9 plus 0 is 9, times -2 is -18, which gives me 0. Woohoo! So these are 2 of the zeros. And now that we have reduced this down to a quadratic, since there's only 3 terms, it's x squared plus 0x plus 9. I just need to solve where this quadratic's equal to 0. So I can think of this as x squared plus 9 equals 0. I can subtract the 9 to the other side. So I get x squared equals -9. Uh-oh, what happens when I square root a negative? Previously, we said you couldn't do it, but in this class, we have talked about I. The square root of -9 is 3i, so I end up with plus or minus 3i. So my zeros are 3, -2, 3i, and -3i. Well, wasn't that fun? All right, one more question. For this rational function, we're going to find all of these things. Essentially, we're going to do all the work to graph it except actually graphing it. So the first thing I notice with a rational function is that we should factor it. That'll help us find almost all of these things. So let's see, what adds to -5 and multiplies to +4? Well, that's going to be x minus 1, and x minus 4. And then x squared plus 9 is a difference of squares, so it factors to x minus 3 times x plus 3. So we're going to use that. Horizontal asymptotes, that's long-run behavior. So I look at the highest powers. X squared over x squared equals 1. So my horizontal asymptote is y equals 1. Vertical asymptotes are divide by 0 errors. So let's look at what makes the denominator 0. Well, x equals 3 will make the x minus 3 equal 0. And x equals negative 3 will give us the x plus 3. We'll make the x plus 3 factor equal 0. Slant asymptotes. Here there are none because we have a horizontal asymptote. You can't have both. You either have a horizontal, a slant, or no asymptote. X-intercepts. X-intercepts are what make the numerator 0, or the top 0, and that's at 1, 0, and 4, 0, because looking at these factors, that's what makes them 0. And then the y-intercept is what I get when I put in 0 to the original function. And this is one of the few cases where it doesn't really matter if you use the factored or the original. I like to use the original because I know when I put 0 in for all the x's, I'm just going to get that positive 4 over negative 9, or negative 4/9. And just to reiterate, that's because if I put 0 in for x, I get 0 squared minus 5 times 0 plus 4 over 0 squared minus 9. 0 times anything is 0, so this just turns into 4 over negative 9. And that's it for this test review. I hope this has been helpful for you.